All right, let's do it. This is a fractional distillation. I have my screen there, so I have a camera here, and I have my tablet here. So I'm going to just start joining my own meeting for the time being. Let's see. So let me start. So let's see. So let's do a screen share. All right, so it's a fractional distillation versus the simple distillation. So in the previous experiment, you did simple distillation. So simple distillation, we had ethanol, and then and then water mixture. And this was hard to separate because, when you had ethanol, so you have, let's say, boiling point, or no, let's say just the temperature versus time. The as time of heating, as you heat the ethanol, you didn't really see the temperature change, but then all of a sudden kind of going like this and then just went like this. In reality, for ideal situation, you have like this, and then all of a sudden, it just goes like this and it goes like this. All right, because whatever the temperature that reaches at 78 degrees for ethanol, you have, temperature reaches 70 degrees and then it goes up and then goes like this for 100 degrees. Ideally, but it wasn't the case. In reality, what happened was the temperature kind of went from 20 degrees and just went like this, and then just went kind of go like that, and just kind of go like that, right? So, so you didn't really see the actual, it's a gradual temperature change is what you saw. So remember, this was the gradual temperature change, and which means that if it forms the azeotrope, so both, all right, both ethanol, ETOH, and water comes out evaporated together, which we don't want. So in that case, so what should we do? We can use fractional distillation. We can use fractional distillation. And fractional distillation, what is it? Well, you use Vigoro column, but fractional distillation, you use the Vigoro column. So Vigoro column, well, you can call it fractional distillation column, but what it looks like is that you have a column that has a lot of pins inside, like this. So you attach this fitting with a lot of pins going inside between your round bottom flask and the three-way adapter. So Vigoro column goes in between here. So you attach a Vigoro column, or you can call it fractional distillation column. You attach that, and then you have your condenser tube and cooling water down and cooling water out, and then you have your vacuum adapter, and you just collect your sample, and you have your heating mantle. So this is the fractional distillation column, so I'm going to call it FD column. Right? Fractional distillation column. Now, what does it do? So basically, inside here, you have your vapor. So I'm just going to use a, this kind of color, right? So you have your vapor mixture. your case, you have, let's say, for the sake of argument, let's say you have toluene, so you have CH3, and then you have cyclohexane, right? So both of these are similar hydrocarbons. So these are hydrocarbons. So they would also form a, like azeotrope because their vapor pressures are similar. Either way, so their boiling point is similar, and then also vapor pressure is similar. So they're going to boil off together. They're going to evaporate together. So in simple distillation, these vapor will go up. But so this vapor will go up. Now, simple distillation, you have cyclohexane and you have toluene. Both of these will go up together, and then they will go up together, and they will travel together because, their boiling points are, not the same, but similar. And their vapor pressure is similar. Again, you don't know what the vapor pressure is, but in a way, they just travel together, right? Now, this is the simple distillation versus fractional distillation. You would have something like, you have pins like this, right? You go like this. I go like this. In fact, turns out that outside of this column, it has a. In fact, I'm gonna just use something different color. Maybe use white, and I'm just gonna color up. So I'm just gonna color here. So then make it bigger so that it actually has a hole. So if you look at it, it looks something like this. So now it's sort of like a glass. There's a glass column, and then you push, from outside, the outside wall is pushed inward. So it would look something like this. So basically, it would look something like this. All right. So meaning that, you have the cold air, is accessible into here, all right, which is fine. So you have a cold air. So now what happens is that surface of this Vigoro column is colder, right? So you have cyclohexane, all right? You have cyclohexane and you have toluene. And they evaporate together. They evaporate together. And once it hits here, that's fine. And it's gonna, go back, and then this, goes back, and then gets, continuously being heated. So this goes up again, and then it hits here. And this one goes up again, it hits here. Now, this goes back down because it's cool, so it gets recondensed, and then goes down here. And this one also gets recondensed, it goes down here. So it goes up and then goes down, and then this goes up and this goes down. Well, but what's the difference? Difference is this. Now, let's say, you have liquid to gas phase, all right? And you need heat. You need heat for this to happen, right? This is, you need heat. So this means, this is endothermic process because you need heat, right, for the reaction to take place. Now, so the reverse reaction would be, so you have a cyclohexane and then gas going into cyclohexane liquid. Reverse process would be exothermic. In this process, delta H, the enthalpy of reaction is, roughly it's minus 33 kilojoules per mole. This is exothermic because if it's endothermic for the liquid to become gas, that's endothermic, and that's, it requires, so you need about 33 kilojoules per mole of energy for the cyclohexane liquid turns into cyclohexane gas. But reverse reaction gas condensing down would release the heat by 33 kilojoules. The toluene gas going into toluene liquid, and this is liquid, and then in this case you have delta H. Again, it's exothermic, but it's like minus 37 kilojoules per mole, right? So in this case, you have 37 kilojoules of energy being released. So if you go back here, when it condenses down, so let's look at this process. So this one goes down into here. It releases roughly about 37 kilojoules per mole of energy is being released. That's good, because that energy is used to evaporate cyclohexane. Now cyclohexane goes up. So now cyclohexane is liquid, but now cyclohexane, this energy, it requires about 33 kilojoules to go from liquid to gas, which means that this energy is used to re-evaporate, and it's a little bit easier for the cyclohexane to get re-evaporated. Of course, 37 kilojoules of energy can be used to re-evaporate, right? Going from liquid to gas. So, to toluene liquid to gas, liquid to toluene of gas is, it's plus 37 kilojoules per mole. That energy is released, but then that energy is used. So it's an overall net change would be 0, which means it's a little bit easier to re-evaporate because the more energy is available, that energy available heat can be further evaporate the cyclohexane. So as a net result, cyclohexane migrates. Repeating this process would cause cyclohexane to migrate much more readily than toluene would go up. They still go up and down, but remember, it goes up and then recondenses. But some of the cyclohexane will go up, and then so they go up and condensing back. They're going up and condensing back. They're going up and condensing back. And they are repeating this process, but cyclohexane would migrate by repeating this just tad faster. But if you repeat this process, eventually cyclohexane will migrate before the toluene, and cyclohexane enters into the condenser tube before cyclohexane would migrate into condenser tube before the toluene. So therefore, what you get at the end would be predominantly, in this case, cyclohexane first. So keep that in mind. So how do we test it? Well, testing, you use something called refractive index. Again, refractive index, how do we use it? All right, refractive index for toluene is roughly about 1.497 or so, and then cyclohexane is like 1.4465 or so. So let's say the mixture happens to be, mixtures, refractive index happens to be, let's say 1.4, 7 or something, 470 or something. So then it's a mixture of these two, and each one is based on mole fraction. Remember, mole fraction, mole fraction, I don't know if you know this, but if you have, let's say mole fraction of species A is based on number of total moles. So each one is, moles of A, and then this one's moles of B. So in this case, you have mole fraction. We call, let's say we don't know how much the toluene is, but we call the toluene as mole fraction of toluene. So it's equal to, let's say, mole fraction of toluene, right, which is 1.497, and then plus, and then mole fraction. So the other one is, 1.0 minus 1.0. Well, you can just call this 1. I'll just call this 1. I just call this 1 minus mole fraction of toluene times 1.4465. Now, this part right here, it says toluene right here, toluene. But this right here, in reality, this is actually mole fraction of cyclohexane. So keep that in mind. That, mole fraction of cyclohexane is, because the whole thing is equal to 1. 1 means pure, right? So you have a fraction. So 0.6 mole fraction, let's say, is 60%. 1 means 100%. So keep that in mind. Now that said, let's erase that because you probably don't need this. All right. So then this part right here is, cyclohexane is, 1. Well, cyclohexane, mole fraction of cyclohexane plus mole fraction of toluene is equal to 1, right? Because it's a fraction. So keep that in mind. So in this case, right? So this case, 1 minus mole of, mole fraction of toluene, right, is equal to mole fraction of cyclohexane. But because you are solving for mole fraction of toluene, we just use X, and I'll just call it mole fraction of toluene. And then, so after this, you solve, solving for mole fraction of toluene will give you, I'm going to erase this now. Will give you the percentage, all right? The percent toluene. All right, so keep that in mind. So that's how to do it, right? So once you get the refractive index of the mixture, and based on knowing the mole fraction of each one, all right, knowing the mole fraction of each one, you can actually get the composition of what you get. So keep that in mind. Anyways, that's it for the background material. So keep that in mind. All right, then that's it. Thank you very much.